Yeah, so she now works in the ITS. I know she also is a director of Indonesian Polymer. So she's an expert in geopolymer. So she got her doctorate degree from the University of Tokyo, and her master degree from Institute. This is in Indonesia, Bandung, the Technology Institute, both the master and the bachelor degrees. And her expertise include green concrete, waste materials, and concrete durability. And her experience, she worked in the World Bank, at the World Bank, the consultant in the between 2002 to 2004. And she was also works as a lecturer of the University Islam Indonesia in 2000 to 2002. And she got 7 patents, and 1 patent has been granted. And for awards, as you can see, she has already got a lot of awards, like best researchers in Indonesia, and the first prize of the mining at the Minerals Industry Institute Research Award, and the chairman, the discrimination, the silver awards. Yeah, so we would like to welcome Dr. Yani to give us the presentation. So please, the 30 minutes, I will let you know after 20 minutes.
Thank you for introducing me. Okay, I will share my presentations today. Okay, on behalf of the host event, I would like to thank to every participant who is still enthusiastic to join us in the second day. My name is Januarti from ITS Surabaya, as introduced by Luangsan. Today, I will share my experience on using bacteria in concrete mixtures containing high volume fly ash. Include biomass. Let's see the recent data of Indonesian government's plan in 2020 to 2024 to increase the national energy supply. There was a target to reach 35 gigawatt. It implicated the compositions of the source, as it is easier to use coal-fired power plant here. The power plant ratio has increased from 53% in 2015 to more than 80% in 2024. So of course, this makes another problem on coal ash management. On the other hand, the government is increasing also the infrastructure, especially in transportation field, the left side, to make more connections between cities. And this has to be correlated to manage the cost on maintenance, of course. As Professor Nakamura explained yesterday, we have to spend more attention to maintain our infrastructures during their service life. So it is not cheap, because every year it costs around 1.5% from its construction cost. Actually, we have also another problem, is also explained by Sagawa Sensei. The problem on the environment, as reported in 2018 by Ministry of Environment and Forestry. The total emission is dominated by changing the land functions from the cropland to non-cropland to cropland. So it means that we change the function of the land. And we have also a problem on peat decompositions and peat fire. And from the energy sector here, the right side, it also contributes more because of activity from coal-fired power plant. And finally, the left side in the bottom, in the cement sector, cement productions contributed more than half emissions in industry sector. As we can see, the increasing of cement production in line with the increasing of national infrastructure plan. Here, we face some problems to be solved. We must decrease the emissions and consider the environmental problem. In concrete industry sector, sometimes using river sand is not recommended because of instability of river in some places. As we are in a tropical country and have a very long coastline, of course, durability and hot concreting are also the additional problems. Then let me show you our experience to utilize collage as much as possible to solve this problem. We increase the utilization of fly ash in concrete as a main replacement, as a cement substitution up to 50% by cement weight. It is not as much as Sagawa Sensei's explanation before, but we have done our best. It has a positive and negative effect to the concrete. It increases the strength at the later age. It has also lowered the porosity and decreased the temperature hydration. However, as a pozzolan, it has a lower strength at the early age and contribute to high shrinkage and makes the workability lower if we use more than 30% by cement weight. We also use bottom ash as a sand replacement up to 25% to get its property on internal curing in the concrete. But of course, it has negative effect to the concrete, very similar to fly ash. And we know that it is a porous material, so it must affect to the higher shrinkage in the concrete. Then we have to find the solutions. We have to find the antidote for the collage effect. So we use microbes in the mixture. In our most experiments, we use Sporosarcina pasteurii as the bacteria for especially for concrete. And then we use these microbes, and also it is found that the microbes created gas as the metabolism product during the casting. So it increased the workability of the concrete during casting. However, it requires lower hydration temperature. So it is less effective actually in concrete if we put high cement content in our mixtures. At the end, our expectations here is having a lower cost concrete with lower porosity and lower hydration, and we have to see if it has a negative effect to the concrete properties. So this is, I have to emphasize here for the microbe selections. Obviously, we have to use non-pathogenic aerobic bacteria. We don't want to get sick because of this kind of bacteria. So it should be non-pathogenic bacteria. And it has to work to fill the pores if the oxygen exists. As concrete containing lime, the pH may a bit higher, and the microbes have to stand high alkalinity. So we isolated the bacteria from lime source, very local place in East Java. This is the reaction occur. I will show you the reactions. When we insert the microbes in the concrete, the carbon dioxide from bacteria can react with portlandite. Okay, there is also the ureatic enzyme, and it reacts with the portlandite to create calcium carbonate. So the calcium carbonate precipitated in the concrete pores to make the concrete becomes denser because it reduces the concrete pores. Okay, I will go to the next slide. We have found that some local bacteria in Indonesia can be very much useful to increase the concrete performance. We have Bacillus subtilis, and even we have also the Bacillus stephensis to produce calcite here. And also, even we can find aragonite in concrete pores. It is a very hard material, and it's a very strong material. It fills the interfacial transition zones in concrete. So there is no gap between the aggregates and the concrete matrix. So we are lucky once during the SEM analysis, we have captured the binary fissions here, the binary fissions of the bacteria inside the concrete. We have also another innovations on using sodium hydroxide to increase the pH of concrete. So usually cement contribute to pH at 12.5 to 13 in concrete mixtures during the casting. By using fly ash and bottom ash, and bacteria may decrease the pH in concrete. So we use a very low concentration of sodium hydroxide of 0.03 molar to be introduced to during the casting, and also as the water substitutions. And it also increased the reactivity of fly ash. And this is, I have also the schematic simulations. This is the internal curing effect from bottom ash that we expect to occur during the hydration of the concrete. It works as a sponge. It absorbs water at the beginning to lower the water to cement ratio and maybe lower the workability. But then it releases moist gradually at the later age. So this is called internal curing. So it contributes the moist to guarantee the next chemical reactions because of the pozzolanic reaction and because of the bacterial activity. And this is a bit complicated, but I tried my best to make simulations. This is the schematic reactions during the first hydrations at the later age of the concrete using bacteria, sodium hydroxide, and the coal ash. And the bacteria produce the CO2, react with the portlandite to produce calcite, and also the fly ash react with the portlandite to produce new calcium silicate hydrate. And at the end, we have a denser concrete, and the bottom ash here still working to guarantee the internal curing inside the concrete during the hardening process. In the next slide, in the next slide, in our experiment, we use a mixed design to obtain the strength of 25 megapascal in 28 days. As a cement replacement, a class F of fly ash was used, and 40% and 50% by cement weight. And bottom ash was used to replace only 10% of standby weight, but it's actually quite a high amount. We made a certain sequence of mixing of the material during the casting. It is very important because it will affect the workability of concrete. We place fly ash first, then mix with the sodium hydroxide, and then continue with all aggregates, and followed by cement and superplasticizer, and also add water containing superplasticizer in the final mixtures, and also we put the bacteria. And also we make a different superplasticizer between the black here. Black is the non-bacterial concrete, and the red here containing bacterial, because we keep the bacterial inside the concrete constant for about 400 milliliter per cubic meter of concrete. And because of the different workability using bacterial and non-bacterial concrete, we make a different content of superplasticizer. For non-bacterial concrete, we put 0.23 by binder weight, and we decrease the amount of the superplasticizer to only 0.1% by binder weight. And we made cylindrical specimen for the strength test and the shrinkage test. We also prepare the cubical specimen for monitoring the hydration temperature in 24 hours after casting. In total, we have 272 specimens, and this is the result. The slump of concrete is something very important to analyze. as the ash content increase in order to achieve good workability for the slump target at 10 centimeter to 14 centimeter. We add water. Yeah, at the end, we add water in the mixture as the fly ash content increase. The ash indeed absorb water during the casting. As expected, bacteria increase the workability of the mixture. So we can see here, and the blue one here, the specimen containing 10% of blast furnace light. And this is the result of temperature monitoring during 24-hour hydrosense. The ash helps a lot to decrease the temperature up to 13%. And something very interesting to see, I use my preview, I use my last experiment in Japan in the University of Tokyo to measure the shrinkage concrete for 10 days. And I put the embedded strain gauge in the center of the concrete. And we can monitor the shrinkage during the hydration of the concrete up to 10 days. As the ash content increase here, we add more water in the mixture, then the shrinkage increases too. But it is very much surprised to see that the specimen with only 30% fly ash and the specimen containing bottom ash show lower shrinkage than the normal concrete. This causes by the ash content and good compatibility and good compacting of the mixture during the casting. And this is also very interesting to see that if we do not control the slump, we just keep the water to cement ratio as it is, constant to our mixtures to guarantee the moist curing, and we have to guarantee the moist curing up to 10 days. We found that there is no difference of using 30%, 40%, and 50% fly ash as a cement replacement compared to the control specimens. And there is a report that using microbes in concrete here, the right side, doesn't affect the shrinkage. So there is no difference using bacteria or non-bacteria in the shrinkage measurement. For the compressive strength at the 28 days, as expected, concrete with the higher fly ash content has low compressive strength. However, at the later age, at 63 days, we found that the increasing rate of the strength is higher than the normal specimen. It is very much pleased to see that the effect of the internal curing by biomass worked very well as the effect of the bacteria to fill the concrete pores during the hydration. And as expected, because of the denser concrete pores, a higher split tensile strength shown by specimen containing bacteria and bottom ash can be shown here in this result. And if we analyze the microstructure of concrete, we found that at the later age, at the ash content increases, the pore becomes denser, so it reduces the pores of the concrete. And especially if we have bottom ash incorporated with the microbes, we'll see the product of bacteria and role of the sodium hydroxide in the next slide. This one. Albite, as a product of aluminosilicate, react with the reaction product between sodium hydroxide and fly ash in the early age, increase as the fly ash presents in the mixtures. The product of bacteria was also found, as we can see that there is a calcium carbonate content in the result, especially with the red specimen containing bacteria. On the other hand, we can see that there is slightly decrease of portlandite as a product of cement hydrations. Why? Because it reacted with bacteria and silicate in fly ash to produce new calcium silicate hydrate and precipitated of calcium carbonate in the concrete pores. And finally, we compare the result of normal strength and higher compressive strength. We found that there is a decrease of CO2 emissions by 44% for all specimen using 50% collage in the mixtures. And the cost of material is also reduced to from 18 to 26%. And it is a very good contribution to the concrete ready mix industry to get the carbon credit actually. And finally, this is the conclusions. As we applied high volume collage in the mixture, we obtain many good results. Yeah, even though we have a slightly lower strength, we can manage that in the future research. We get a lower cost at least, and denser matrix, low hydration temperature, and better shrinkage. If we control the water content is very much important. And of course, we can contribute to sustainable concrete. And Dr. Ruan, this is the end of my presentation. Thank you very much, and I go back to you. I will stop sharing my file.
So then we would like to ask, the question goes to Professor Dr. Yani. So available, are you available now?
Yes, I'm ready.
Yeah. So the first, there are several questions. So one is, I think they are very interested about the bacterial. So that is has already been done. A lot of the researchers are doing that. So the one question is, how long does it take the bacterial to repair concrete? So the time for it has the effect.
Okay, thank you very much, Luang Sang. Actually, my presentations today not talking about self-healing concrete, but I did have another result on using bacteria to heal the cracks in the concrete. Maybe the concentrations of bacteria we use for healing the cracks is not the same as the bacteria I explained today. We have to use maybe like 3 times or 4 times higher than, the amount of bacteria should be higher because of the calcium precipitations, and the healing process will take place in the speed recover other than only using a small amount of bacteria. And usually if we use like a 5 liter per cubic meter, this per cubic concrete, in this my presentation, I use only 400 milliliters. So it is a small amount, only a half liter. But for healing the cracks, we have to use like a 500 milliliter per cubic meter of the concrete. So it will heal the concrete cracks. It's not for the macro cracks, but for micro cracks, because bacteria is a micro and tiny material. We cannot give the responsibility to bacteria to heal the macro cracks.
I agree.
For the limitation is like a 0.3 millimeter for healing for about maybe like a 20 days to 2 months. So it will heal the cracks completely. But in the last my experiment, I conducted the monitoring for about like 100 days, and it heals completely.
Okay.
Thank you for the questions.
We hope that the bacteria can live longer. So if there are another crack occurs, so it can repair again.
Yeah, it is a very healthy bacteria. It has a very long life, even longer than our life. Even after the experiment, even after my retirement, the bacteria is still working, I think.
Exactly. So, and another question is for you is you mentioned in the nutrition, not nutrition. So you use ammonium carbonate. Is that the nutrition for bacteria, or it's used for activator for the concrete?
Okay, thank you very much. The bacteria, the Sporosarcina bacteria I use in my experiment is like the basic of the enzyme is ureatic. So we use like ammonia created from some, how to say, sato in Japan, but it's
Yeah,
it's like a
gross.
sugar.
Yeah, sugar.
The local sugar from plant, from the natural plant in Indonesia, brown sugar actually, and we created the nutrition for bacteria, and then it should be ready for just add to the concrete, just like super plasticizer. But we need maybe like a small amount of water to dilute the bacteria and the nutrients to be added into the concrete, and it's already commercialized, so we can buy it in Indonesia.
Thank you. Quite a lot of questions for our speakers. So another question, maybe still for Dr. Yani, it's regarding the bacterial for concrete. So can you please explain what kind of method do you use in mixing the bacteria in concrete? So in other research, the audience, so he says that he noticed that other researchers, they seal the bacteria in the form of capsule to avoid the early interaction. So in your research, what kind of methodology do you use?
Thank you very much. It's very interesting questions. Of course, as I explained in my slide, that I use aerobic bacteria. So actually we use the spore, not the bacteria, or only the spore. And then we have to avoid the contact of the spore with the air. So because after it contact with the air, then it will grow. I mean the population will grow. It becomes mature, and then create a lot of bacteria, and then will consume up all the nutrients before it works. So it becomes like a bigger population and doesn't work for anything. So just before we need it, we just open the lid of the bottle and then just add it to the concrete. And we have to consider also about using the super plasticizer. So we need sometimes we have to make it like a longer time for the bacteria, or we have to avoid the super plasticizer contact directly with bacteria. So if we put the bacteria first, and then we have to put the super plasticizer in the final casting.
Okay.
If we put the super plasticizer first, and then we put the bacteria in the final casting. So we need some time. Yes.
Okay. We need to avoid
the direct contact with the super plasticizer.
Okay. Thank you. And maybe the last one, though, I ask you now. So it's someone asked you why you use sodium hydroxide with 0.003 the M. So can we use a higher or lower one?
Okay. Thank you very much. Actually, we have to adjust first the pH of the concrete. Actually, I already explained that 12.5 to 13 is the pH, the normal pH of the concrete. But by using fly ash and bottom mass, and also the additional of the bacteria that containing ammonia, so the pH of the concrete will decrease. So in order to keep the pH of the solutions, we have to increase a bit the pH of the concrete. For example, we adjust the pH of the fly ash first. If the fly ash, it is very simple experiment. We mix the fly ash with the water, and then the ratio is 1 fly ash and 4 water, and then we mix that, and we measure the pH. If the pH is lower than 10, and then we have to adjust. We put the sodium hydroxide flake, only small amount, only like a 1 gram or 1.5 gram, just to adjust that the pH will increase to 12 point something.
Okay.
Not too much, because if it is too much, and then it will damage all the So just small amount, and also we have to check again the pH of the fly ash. It's very important. If the fly ash is already in the alkali conditions, I mean it contains a lot of alkali and also some calcium exists in the fly ash, maybe we just use small amount of sodium hydroxide on the concentration maybe not 0.03, only 0.001,
Okay.
or even we don't use any sodium hydroxide to boosting the fly ash reactions. So just to help the pH balance in the concrete juice during the casting.
Okay. Okay. So fly ash also have the variation in pH.
Yes.
Okay.
So we have to check that first.
I see. Thank you. Thank you so much.
Welcome.
So, because the time is approaching, so we would like to finally before the closing, we would like to invite Dr. Yani to address the closing remarks, because she and the group contribute a lot for organizing this seminar. So it's okay, Dr. Yani, for the closing the remarks. Would you please?
Yes, with my pleasure. Good afternoon, distinguished professor, presenters, moderators, and all participants. It is my the great pleasure for me and honor to see the outcomes of this two-day webinar online and to provide my closing remarks. On behalf of Institute Teknologi 10 November and FIB Indonesia as the host, I would like to thank our supports from JSCE, especially to Professor Hamada, to provide presenters from Japanese side. I would like to express our gratitude and appreciations to our presenters. For the first day, Professor Hikaru Nakamura from Nagoya University, Dr. Fadilah Muslim from FIB Indonesia. She presented from Germany, and Mr. Toshimitsu Kobayashi from Shimizu Corporations, and Dr. Bakmun Narantuya from MUST Mongolia, and Dr. Luan Yao from Saitama University. We did enjoy your presentations yesterday. I would like to thank all contributions today from Professor Han Aili, the President of FIB Indonesia, Dr. Yasutaka Sagawa from Kyushu University, and Mr. Takeshi Tochirigai from Kajima Corporations. Thank you for sharing your valuable experience. Special thanks to my best friend, Dr. Luan Yao, and also Dr. Niar, who have prepared this event very well. Being a moderator, operator, and everything, give all your time to make this event become very much successful. To all participants, your attendance, questions, advices to this event has been extremely valuable. I'm very much pleased to see that fruitful discussions today and yesterday and interactions that have advanced amongst the participant and presenter during the past 1.5 days. We have discussed a very important topic on recent advances and practice on concrete that may be expanded to better Asian concrete in the future. There are many challenges that we are still facing in the three countries that are developed towards more global discussions and collaborations to involve more Asian countries to join us in the future. This was also mentioned by Dr. Sagawa in his presentations. We appreciate this event to give us more opportunities to learn in the first day, and more than 600 participants, I think, from 3 countries has been submitted their registrations. More than 200 yesterday joined the first day, and more than 200 joined today. Thank you to all operators who control the Zoom room and the live streaming event on YouTube very well. And thank you, Dr. Yuta Yamada, for your help. Finally, I wish you all good health and hope to see you again in the next JSCE webinar. On behalf of ITS as the host of this webinar, I would like to call the event to close. Terima kasih, Bayer Lala, arigatou gozaimashita. Thank you very much. And we go back to Luang-san.
Okay, thank you so much. Thank you, Dr. Yani, for very, very nice closing remarks. So we hope, like, in the future, we still, like, next year and later, we have more and more such kind of the communications and seminar and and for more collaborations. Yeah.
はい、頑張ります。
頑張ります. Okay, so our friends, our audience, if you have any more questions that not yet mentioned in the discussion, the group, the section, so you can directly let us know by sending email to the organizer. Okay. Thank you so much for our audience for attending here. So see you maybe next year. So bye-bye.
Bye-bye.
Bye.
Thank you very
Bye-bye.
much.
Thank
Thank you
you.
very much.
Thank you very much.